In the first section of Chapter 5, we looked at various financial models that used simple interest. Simple interest is interest that's paid only on the principal that was invested or borrowed, but it's much more common to have compound interest, where interest is paid or charged on the interest that accrues. At the beginning of this section, you see a table which compares simple interest and compound interest. The simple interest is on the left, and as you can see, we multiply the same amount, $1,000, times 5% every time. But on the right side, with the compound interest, every time we calculate the interest, we use the total balance that has accrued to calculate the next interest calculation. And so simple interest allows money to grow faster. Your first checkpoint for this section is to complete 2 more lines of the compound and simple interest table that you see here. Okay, let's get started with some examples. If $7,000 is deposited in a savings account that pays 4% interest compounded annually, how much money is in the account after 9 years? So our present value is $7,000. Our interest rate is 4%, which we write as 0.04. Remember, we always use a decimal when we're calculating with the interest rate. And our time is 9 years. And I'm going to write down one more thing for compound interest. We need to remember our compounding time is annual. Okay, so the interest is paid once a year in this situation. So we're going to look first at what we would get after 1 year. We would have $7,000 plus 4% of the $7,000. And I could rewrite that as 7,000 times 1 plus 0.04. Or even a little more simply, I could take the plus out and just write 1.04. And this gives me a figure of $7,280. So in 1 year, we would get an additional $280 on this account. But now to calculate for the second year, I don't start with the 7,000. I start with the 7,280. And again, I'm going to multiply that by 1.04. And this gives me now $7,571.20. Okay, now it would be very tedious to do this 9 times. So what we can do, instead of doing that, we're going to multiply by that 1.04 9 times. So we're going to write that as an exponent, 1.04 to the 9th power. And this gives us a total of $9,963.18. And remember, when we're working with financial problems, we always round off to the nearest cent. So after 9 years, I would have just a little shy of $10,000 in this account. So just for reference, the future value is equal to the present value times 1 plus I, which is the interest rate per compounding period, to the n power, where n is the number of compounding periods that we're going to invest the money. Okay, contrast this with our simple interest formula, where we have future value is equal to present value times 1 plus RT. I'll make these a little easier to compare. I'm going to put the R here and the T up here. So here I'm multiplying by T, but here I'm using T as an exponent. And that is the primary difference between simple interest and compound interest. Let's look at another example. Suppose $1,000 is deposited for 6 years in a savings account paying 8.31% per year, compounded annually. So let's write down our pertinent information. Our present value is $1,000. Our time is 6 years. Our interest is 8.31%. And just in case you're not aware, this is ridiculously high. You can't get an account that's going to pay that much. And our compounding is annual. Okay, the first thing they ask us to do is to find the compound amount. So the compound amount would be, let's use our future value formula. When they ask for the compound amount, this is what they're asking for. So this would be 1,000 times 1 plus I. Let's just change this to 1.0831. And since it's annual compounding for 6 years, this is going to be 6. And when I multiply that out, I get $1,614.40. And then it says find the amount of interest earned. The amount of interest earned is really pretty simple. You take how much you ended up with, subtract how much you started with, everything else is interest. So 1614.40 minus 1,000 means that I made $614.40 in interest on this investment. Pause the video now and work on checkpoint 2. We can find out a lot more than just the ending balance of an investment using this formula. If we have all the other pieces, we can solve for any other piece that happens to be missing. For instance, if a $16,000 savings account grows to $50,000 in 18 years, what is the interest rate assuming annual compounding? So we start with our present value is $16,000. We don't know our interest rate, but we do know that the time is 18 years. we know that our future value is going to be $50,000. And we're using annual compounding. Okay, so start with the same equation. And we'll substitute in 50,000 is equal to 16,000 times 1 plus, I don't know, and it's going to be compounded n times, which is 18. The first thing I'm going to do is divide both sides by 16,000. That gets rid of this. That gets rid of a lot of this. And this gives me 25 over 8 is equal to 1 plus I to the 18th power. And we're going to change this to a decimal, which makes it 3.125. And then to get rid of this 18th, I'm going to take the 18th root of both sides. So I'm going to have to use the calculator to get the 18th root of 3.125. And that will be equal to 1 plus the interest rate. Okay, and then I can just subtract 1 and move my equal sign over. And this comes out to approximately 0.06535. So the answer to the question of what is the interest rate changes back to a percent, 6.535%. Okay, make sure that you know how to do these higher order roots in your calculator. Some calculators are a little different, so you might have to practice a little bit. Let's look at another example. In July 2016, Bankrate.com advertised a money market account at Ally Bank at an interest rate of 0.85%. Find the value of the account if $10,000 is invested for 1 year and the interest is compounded. And here they give us 5 different situations. These are the most common compounding periods. We've already worked with annually, but there's also semi-annual, quarterly, monthly, and daily. So we're going to see how much it changes our end result if I change the compounding period. But let's start with what we know already. Our present value is $10,000. Our interest rate, it was 0.85%, so it's going to be even smaller as a decimal, 0.0085. Our time is 1 year. And we'll start with annual compounding. Okay, so annual compounding for investing for 1 year is a lot like the simple interest. So we're going to have 10,000 times 1 plus 0.0085. And for annual, this will be 1. So this is just 1.0085 times the 10,000. So I'm going to get 10085. I have to move my decimal point over 4 places to when I multiply there. So I get $10,085 using annual. Now let's look at semi-annually. This is still $10,000 and 1 plus. This is where it changes. Because I'm getting the interest semi-annually, I only get half of it in one compounding. Okay, I don't get this twice a year. I get half of it twice a year. Okay, but then I can change this from a 1 to a 2. And I get $10,085.18. So by doing 2 compoundings instead of 1, I make an extra 18 cents. Let's look at the next situation, which is quarterly. Quarterly means 4 times a year. So 0.0085 divided by 4 raised to the 4th power. And this is going to give me $10,085 and 27 cents. So you can see here, for 1 year, the difference between annual and semi-annual is 18 cents. And the difference between semi-annual and quarterly is only another 9 cents. So for most people, this kind of investment, it doesn't really matter how often it's compounded. The change is very small. I'm going to keep that last number up here. Quarterly was $10,085.27. Now let's look at monthly. So now I'm going to have 10,000 times 1 plus 0.0085 over 12 to the 12th power. And so this gets me $10,085 and 33 cents. So you can see here I made a gain of 6 cents by going with monthly compounding. The last one they ask us is about daily compounding. And for daily, we need to divide by 365 and raise it to the 365th power. And this gets us up to 36 cents extra. So going from monthly to daily earned me an extra 3 cents. Pause your video and work some problems similar to this in checkpoint 3. Now, after looking at that last example, I'm sure some of you are thinking, well, what's the point of compound interest? It doesn't really get me very much more. And this is true in that particular problem because we only invested the money for 1 year. Okay, the true power of compound interest is to invest money over a much longer period of time. For instance, if you are saving for retirement or for something else that's on down the line, like a child's education, compound interest can really grow your savings much quicker than simple. Let's look at another example. Okay, it says suppose $5,000 is invested in a savings account at an annual interest rate of 3.1%. So my present value is $5,000 and my interest rate is 3.1%. My time is 4 years. And now we have a new compounding period called continuously. You saw in the last example that when my compounding period gets shorter, that my earnings do increase somewhat. And so following that idea all the way to the end, what if I made my compounding period extremely short, a millionth of a second? Would I get more money? I would. Okay, because I'm getting interest recalculated every compounding period. And it's just a little bit more, just a little bit more. But I have a lot of them. So let's see how this affects it. We have a different equation for this. And we use our old friend E. So for continuous compounding, the future value is equal to the present value times e to the RT power. So looking at this situation, I'm going to have my future value is equal to 5,000 times e to the 0.031 times 4. And I would strongly recommend that you calculate this first, then find e to this power, and then multiply by the 5,000. And my end result is, after 4 years, I'd have $5,660.08. Pause your video now and work on checkpoint 4. Okay, we're going to look now at some ordinary corporate bonds. Sometimes these bonds pay simple interest semi-annually. Sometimes these bonds pay simple interest semi-annually. But there are also bonds called zero coupon bonds, where the interest is allowed to accrue and is only paid at the maturity of the bond. Let's look at an example of this. Doug bought a 15-year zero coupon bond paying 4.5% interest, compounded semi-annually, for $12,824.50. What is the face value of the bond? Or in other words, what is the bond going to be worth when it matures? So let's write some things down. The time is 15 years. The interest is 4.5%. And the original price, or the present value, is $12,824.50. And we're asked to find the future value, or the face value of the bond. So we're going to do just like we've done before. Future value is equal to the present value, $12,824.50 times 1 plus 0.045 divided by 2, because we're paying semi-annual interest, But it's 15 years and we're getting twice a year, so that's a total of 30 interest payments. And this gives us $999.618. So we're going to round that off and say that the face value was $25,000. Pause the video now and work on checkpoint 5. Another thing we can do with the future value equation is predict how long it will take for prices to reach a particular level, or how long it will take for us to save a specific amount of money for a long-term goal, say a child's college education or perhaps even our own retirement. Let's see how this is done. So suppose that the inflation rate is 3.5%. So I'm going to write that as interest even though it's not interest. 3.5%, which means the overall level of prices is rising 3.5% per year. How many years will it take for the overall level of prices to double? So I want to know the time. And when it says the level of prices to double, I don't have specific money values, but I can pick, say, $1. How long will it take $1 worth of goods to be costing us $2? So I can use for my future value 2 and my present value 1. So now I've got 2 is equal to 1 times 1.035 and to the t power. So I don't really need that 1 there, I'll just erase that out. And now to solve this equation, I'm going to go back to something I learned in chapter 4, and that's to take the natural log of both sides. So now I have natural log of 2 is equal to natural log 1.035 to the t power. And since this is now a logarithm, I can move this t right here and then divide by the natural log 1.035 on both sides. So here's my t, and I see that this comes out to 20.14879. So it's going to take a little over 20 years for prices to double if the inflation rate remains at 3.5%. Pause the video now and work on U try 6. When we start using different compounding periods, it may become difficult to compare two different opportunities and see which one is really the better. To do this, we can find for each opportunity the APY, or the annual projected yield. And this is a way that we can compare apples to apples and know which account is actually going to give us the best outcome. So, in July 2016, American Express offered its customers a money market savings account at a rate of 0.90%. Assume the account compounded interest daily and the principal is $100,000. Find the APY. So my present value is 100,000. My interest is 0.90%. So it's going to be 0.0090. Okay, and we are compounding daily. So the APY is really the simple interest rate that is equivalent to our compound interest rate. So we're going to use an equation that compares those two. So we start off with 100,000 times 1 plus RE, and that is the effective rate. And we're going to let that equal 100,000 times 1 plus 0.0090 divided by 365, since we're compounding daily, and then raised to the power of 365. Okay, and we can just cancel out the $100,000 on each side, which gives us 1 plus RE equal to 1 plus 0.00990 over 365 to the 365th power. And then I'm going to move this 1 over here. So this is my effective rate, and it comes out to approximately 0.00904. So instead of 9%, we're getting, or 0.9%, we're getting 0.904% is my APY. So we could write this equation that we used like this. R sub E, which means the effective rate, is equal to 1 plus the stated rate over the compounding periods raised to the number of compounding periods minus 1. So this is my effective rate, or my APY. Another very popular investment tool is a money market account. Let's take a look at how those work. When interest rates are low, as they were when this text went to press, the interest rate and the APY are insignificantly different. In the last example, we saw that the difference was very, very small. To see when the difference is more pronounced, we will find the APY for each of the given money market checking accounts, which were advertised in October 2008, when the offered rates were higher. So we've got one from Imperial Capital Bank, and it's 3.35%, and that's compounded monthly. And then we have a second account that's 2.33% compounded daily. Okay, so this one is a lower interest rate, but it's compounded much more often. So it makes it difficult to compare these without referring to the APY. So that's what we're going to do. So here again is our equation. The effective rate is equal to 1 plus R over M to the M power minus 1. So for the first one, we're going to have 1 plus 0.0335 compounded monthly, so over 12 to the 12th power minus 1. And this comes out approximately 0.03419. Now for our second account, we do the same thing. R sub E is equal to 1 plus 0.0233 over 365 to the 365th power minus 1. And this is approximately equal to 0.023572. So we see in this case, there's not enough difference between the monthly and the daily compounding for this to be a better deal. So this is going to be my better deal for these two money market accounts. Let's pause the video now and work on checkpoint 7. Let's work another set of problems dealing with APY. This time we'll compare 3 different banks. So Bank A has a 3-year money market account, so T is equal to 3, with a 1.80% interest rate, and it's compounded annually. Okay, so this is Bank A. Bank B has a similar account, and it doesn't specify, so I'm going to assume it's also a 3-year account. The interest is 1.77%, and this is quarterly. And then Bank C offers 1.75% interest, and it's compounded monthly. Okay, so now these interest rates are a little bit closer than the ones in the last problem, so we might find one that's a little bit better, even though it's a lower interest rate. So let's look at the first one here. And I've got 1 plus 0.018 over 1 to the first power minus 1. And so this is going to equal 1.80. So this is going to equal 0.0180. So the interest rate is 1.80%, the APY. So let's look now at the second account. This is going to be 1 plus 0.0177 over 4 raised to the 4th minus 1, which gives us 0.0178 or 1.78% APY. And then my third choice, 1 plus 0.0175 and we're compounded monthly, so divided by 12 to the 12th power, and this gives us 0.0176 or 1.76% APY. So again, even though we're compounding more often, it's even with these interest rates pretty close together, it's not enough to make one better than the other because of the more frequent compounding. You've got a problem similar to this at checkpoint 8. Let's pause the video and do that now. Okay, we're going to look now at planning ahead for a lump sum that's due sometime in the future. This might be the balloon payment on a mortgage, or maybe it's the down payment that has to go with leasing a car. It says Keisha Jones must pay a lump sum of $6,000 in 5 years. What amount deposited today at 6.2% compounded annually will amount to $6,000 in 5 years? So Keisha's trying to plan ahead. She knows she doesn't have to have the $6,000 right now if she can have some lesser amount and let it earn interest until her debt is due. So we're going to say now that the future value is the $6,000. The interest is 6.2%, and our time is 5 years, and we are using annual compounding. Okay, so we're going to have 6,000 is equal to our present value, which we don't know, times 1.062. Since we're using annual compounding, you can just add 1 to this, and we want to know what's going to happen in 5 years. So now we can take all of this and put it over here. So our present value is equal to 6,000 divided by 1.062 to the 5th power. And when I put that in the calculator, I end up with 44, 41, 49. So if she can get something that's going to give her the 6.2% return, she doesn't need $6,000. She only needs a little under $4,500 to save up so that she'll have the money when she needs it. Pause your video now and work on checkpoint 9. In this example, we'll be looking at present value for something where the future value is known. In this case, a zero coupon bond. So it's a zero coupon bond with a face value of $15,000 and a 6% interest rate compounded semi-annually will mature in 9 years. What's a fair price to pay for the bond today? So we know that our future value is $15,000. Our interest is 6%. And our time is 9 years. We also know that the interest is compounded semi-annually. So we're going to write out our equation. 15,000 is equal to our present value, which is what we're trying to find. How much should I have to pay for this bond right now. And it's going to be 1 plus 0.06. And since it's semi-annual, we divide by 2 and raise to the second power. No, we don't raise to the second power, because how many times will we get this interest payment? Twice a year for 9 years. So this is the 18th power. My apologies. So now we can take all this, put it under the 15,000. So my fair present value would be 15,000 over 1 plus 0.06 over 2 to the 18th power. And again, I would not recommend that you try to put this in the calculator all at once. It's very easy to make a mistake, and then it's very hard to figure out where the mistake was. But when you calculate all of that, you see that a fair price for this bond would be approximately $8,810 and 92 cents. So pause the video and work on your own similar problem to this one in checkpoint 10. One last application we have for this equation is to figure out problems dealing with the inflation rate. This helps us to understand how much things cost in the past and how much we might expect to have to pay for them in the future. So the average annual inflation rate for the years 2012 to 2014 was 1.72%, and we can use that as our interest rate. So it's 1.72%, and they gave us for the years 2012 to 2014. So my T is going to be 3 years. And they give us, at the end of the time, a price of $1,000. So that is our future value, because it's the value at the end. And they want to know, well, what did it cost 3 years before? So that'll be our present value that we're trying to find. Okay, so since we're trying to find present value, we'll write that over here. And we have future value divided by 1 plus I to the n power. So 1,000 over 1 plus 0.0172, and the third power, since we had 3 years that this was calculated over, and this works out to approximately $950.12. So something that cost $1,000 in the early part of 2015 could have been had for about $950 at the beginning of 2012. Okay. Work your last checkpoint now, and then go on and work on your homework assignment.